Hi, everyone. So in this lecture, we're going to give an example of a divide and conquer algorithm. In the next 3 lectures or so, we'll give several examples, but let's start with a sorting example. And so this is merge sort. The problem is well known, and probably for many of you, you know the algorithm as well, which is given a list of numbers, sort them in ascending order. Now, the list will write as A, 1 to N. So it has N entries in it. And the merge sort algorithm is simple enough that I can just give the pseudocode and then we'll fill in the details of it. So the function takes as input an array of size N and outputs a sorted version of this array. So as long as the array has length more than 1, we do the following. We break the array into 2 pieces, the left half and the right half. We call recursively merge sort on each half, and then we merge together those sorted arrays. And the base case is instead that we just return the, in the case where the array only has 1 element, we just return the array because it's already sorted. So we obviously have to fill in this merge operation, right? It makes sense that I split the array into 2 pieces. The first one going from 1 to the floor of n over 2, the second one floor of n over 2 plus 1 up to n. But how do I now do the merge? So let's say I have 2 sorted arrays. Let's call them X, which has K elements in it, and Y, which has L elements in it. How do we merge them into a sorted array, Z? The key thing to observe is since X and Y are sorted already, the smallest element in Z is either the first element of X or it's the first element of Y, because those are the smallest element in X goes first, the smallest element in Y is first, and so one of those 2 has to be the smallest in the combined array. And so this is exactly how the merge idea works, which is that, let me just write it. So first element of Z is either X1 or Y1, whichever is smaller. And so basically, to merge together X and Y, we can just pull off the smaller of the 2 first elements. Then we're left with some remaining parts of those arrays, X and Y, and then we just recursively apply it. So Z can be recursively constructed in this manner by just repeatedly pulling off the front element from X or Y, the first one, that's smaller. And so we let this circle denote concatenation, and it just operates as, for example, if I do, I don't know, 3, 2 concatenated with 4, 7, that just returns the array 3, 2, 4, 7. So that means that we can write out the merge function, which again, it has a base case or 2 base cases in this one. So if X is empty, then the merge should just return Y. Similarly, if Y is empty, if its length is 0, then we should just return X. Otherwise, we compare the first elements of X and Y. If X is the smaller element, then we put it first. And then what's left is just merging X from 2 to K, that's what remains of X, and all of Y. Otherwise, if Y is smaller, then we do the same thing. We merge all of X with what remains of Y. So it inputs 2 sorted arrays, this function merge, X and Y, and it outputs a single merged sorted array. We'll call it Z in this case. We can ask, how long does this merge algorithm take? Because to figure out how long merge sort takes, we've really got to figure out what merge is doing, right? That's the bulk of the computation other than the recursive calls to merge sort itself. So the runtime of merge, we should think about what happens in lines 1 through 5. We just have a constant amount of work, right? We evaluate 2 if statements and then we make a comparison. So we have constant, let's say 01 time per recursive call. And then how many recursive calls do we get? Well, we're only going to execute one of lines 6 or 8. And when we execute it, one of the 2 inputs shrinks by 1, right? So it started out, there was K plus L entries in X and Y combined. After 1 recursive call, now there's K plus L minus 1. And so after K plus L recursive calls, we've shrunk down to the base case, at most that many, right? It might actually keep pulling off of X and actually terminate after only K calls, but we know that it can't go more than K plus L times. So terminates in at most K plus L recursive calls. So we get the runtime of merge is big O K plus L. In the case where X and Y are both of length N, then this runs in big O of N, right? Because you just get 2N, the 2 gets absorbed into the big O. So it's a linear time algorithm. So now what's the runtime of merge sort? If we look at what happens in merge sort, let's go back up to it. There's really nothing other than that operation, right? So we have an if statement that's order 1 time to evaluate, and then we just call merge on the 2 recursive calls. So we're going to get in one execution of merge, it makes 2 recursive calls. Each one is on an input of half the size. And then we have the time to like identify and combine the answers is merge, which we've just characterized the runtime of. It's going to be big O of N in this case. So let's write it out. So we can write the recurrence relation as to the time to run on an input of size N is just 2. We make 2 recursive calls, each on size N over 2, plus big O of N to combine them. So in this is, and really, I guess I should have well, the first, yeah, I'm missing the floor or the ceiling here, but it doesn't actually affect anything, right? The first array, it goes from the floor of N over 2, and then the second one might be 1 more, but this won't impact the runtime. So I could just write this as the floor of N over 2 if we like. So this is the merge. We call merge sort for 2 arrays, size N over 2. And this one, I meant to write that in blue, but this is merge 2 N over 2 arrays. So big O of N over 2 plus N over 2 equals big O of N. And so now I look this up in the master theorem. Which we went over last class. We have A equals 2, B equals 2, D is the power on n here, D equals 1, and you get T of n equals big O of n log n. And that's the overall runtime of merge sort. Which is quite nice, right? We're able to merge two arrays in n log n time. Or sorry, we're able to sort one array in n log n time. To do this, we use this merge operation. Apologies. Okay, let me give you an example just to show you like what happens in these recursive calls. I think probably many of you are already familiar with this algorithm, but I think it's useful just if you're still kind of thinking about how recursive algorithms work. So to avoid writing as much, I'm just going to write, let's say we call merge sort on this array A, which is 4, 9, 6, 2, 8, 1, 4, 3. So what happens? It calls merge of merge sort on the first half, 4, 9, 6, 2. Merge sort on the second half, 8, 1, 4, 3. This then performs these recursive calls, right? We get these pieces. So on this one, we call merge on merge sort of 4, 9, merge sort on 6, 2. And on the right side, we get merge sort on 8, 1, merge sort on 4, 3. And this then again makes recursive calls for this one and this one and this one and this one. Here, we're just going to get, when we split this into two arrays, they're of length 1 and they're already sorted, right? We're going to get merge sort on 4, merge sort on 9. That then just returns the array itself. So here we're just going to get merge on 4, 9, merge on 6, 2, merge on 8, 1, oops, 1, and merge on 3, 4. Right? And so now let's evaluate these things. So when merge gets called on 4, 9, it returns exactly 4, 9. This returns 2, 6, 1, 8, 3, 4. Now we go up a level. We merge. These are the sorted arrays here that then get merged again. So we pull off the first elements. It's going to go 2, 4, 6, 9. This one, pull off the first elements. It's going to go 1, 3, 4, 8 when it's merging these two sorted arrays. 1, 3, 4, 8. And then again, now I've got two sorted arrays. I merge them by pulling off the first entries. It's going to go 1, 2, 3, 4, 4, 6, 8, 9. All right, so these kind of come back up. Like that. And that's the final result. Okay. One note, right? This is kind of an aside. I'm just writing this or letting you know. So many of the things we're writing here in this course are recursive implementations, right? So recursive algorithms call themselves within their execution. In some programming languages, including Python, which we're using basically just for convenience, recursive calls are not optimized. And so each time we make another recursive call, it adds a new stack frame to the call stack. The call stack has a limited depth. And at some point, if we try and just do an implementation of these recursive algorithms, we'll hit the max recursion depth. And actually Python will stop. You can increase it, but Python's not really optimized for these recursive implementations. There are other languages that have what's called tail call optimization, and they handle recursive calls properly without adding it to the stack. And then these can be like the most efficient implementations of algorithms. But you can always unwrap this recursion and rewrite it as an iterative algorithm. And so if you're interested, just take a look online. For example, even on Wikipedia for Mergesort, there's an iterative implementation listed. And it has the exact same idea. It's not quite as clean. Like these recursive algorithms are really elegant in some ways. It just depends on the language you're trying to implement it in. So I just wanted to mention that as an aside. Now, with Mergesort, we achieved big O of n log n runtime. There's then this question, can we do better? And the answer in some sense is no. And I want to try and give an argument for that. And so these are really tricky arguments in general, because what you're trying to say is that there cannot exist an algorithm that performs better than, let's say, Mergesort in terms of its asymptotic runtime, big O n log n. And it's hard because you're trying to eliminate the possibility of any algorithm existing. And so this result is kind of just an indication. It gives us some insight into why we can't really expect to do better than n log n. Mind you, we can still possibly improve the constant in front of that n log n. And in the assignment, and actually in the next question, or in the next lecture, we'll talk about medians, which then leads into quicksort, which practically is runs faster than Mergesort, but it doesn't have a better asymptotic runtime in any sense. So let's consider any sorting algorithm that operates by comparing elements in the input array. That includes most sorting algorithms, but not every possible sorting algorithm. So as an example, if you think about where's the meat of Mergesort, it's exactly this line 5, right? It's in merge, we compare two elements. Everything else is just these recursive calls deciding on which ones to compare, right? But we just make these comparisons. This then creates a reordering, and then that propagates, over and over again. So if we're operating by these pairwise comparisons, we can think of a comparison tree. So let's say we take as input an array of length 3. Has the elements A1, A2, A3 in it. And it could be in any order, right? And you don't initially know which order they're in. So the comparisons that you might have to make, we can think about writing it in a tree. You can ask, is A1 less than A2? If the answer is no, then you need to ask, is A1 less than A3? Or you can ask if A1 is less than A3. So let's say the answer is no, or the answer is yes. I'm going to go down the no branch first. If the answer is yes, so we know that A2 is bigger than A1, A1 is less than A3. That then actually specifies the order of the array, and we would get yes, and we would return A2, A1, A3 as the sorted array. So I'll put that in a square here. That's a kind of a terminal branch. If it's no, then we don't yet know whether A2 is less than A3 or not. We have to do one more comparison. So A2 less than A3. And if that's true, then, well, there's the two options. If the answer is no, or if the answer is yes. If it's no, we get the ordering A3, A2, A1. And if it's yes, we get the order A2, A3, A1. And you can check this after that I'm writing this correctly. But if you follow, one leg here, we know A2. So we asked, is A1 less than A2? The answer was no. So A2 is less than A1. A3 is less than A1 because we got a no on this branch as well. And A3 is less than A2. And so that means that A3 has to go first, then A2, then A1. On the yes branch, we get the same kind of comparisons going on. So we can then ask A2 less than A3. We either get a no or a yes. Get a yes, that's enough to actually specify it. If we get a no, we have to do one more comparison to figure out if A1 is less than A3. In this case, we get A3, A1, A2, and in this case, we get A1, A3, A2. Okay. Like that. And then these are all my kind of comparisons. Okay, kind of complicated tree, but the point is that, I chose arbitrarily here which one to compare first, A1 less than A2. And then similarly, there's different comparisons I could make here. I could ask instead A2 less than A3 next. And so that's what a sorting algorithm can decide on, is which comparison to do next. But you can see that in the worst case, I keep getting the answer that gives me the minimum amount of information about the array, no matter which one I put first. And so the depth of this tree is the number of comparisons I would have to make in the worst case to identify the ordering of the array. So the depth of the binary tree gives the max number of comparisons that could be required to sort. In this case, the number of possible orderings is 3 factorial, right? There's 6. And if you look, there's 6 of these boxes, right? The 6 possible orderings of the array. And so basically, all we can do in a sorting algorithm is rearrange these comparisons on the tree. I realize this is kind of an abstract argument, but I'm trying to give you some insight into why n log n is really the best we can expect. So how could I don't know how to arrange these in the tree. That's what the algorithm is trying to decide. There's many possibilities for it. But what I can just look at is just like, how many nodes are there in this tree? And no matter how I arrange it, how deep will this tree have to go in order to put all the possible comparisons on it? Because any algorithm may have to perform any comparison. So an array of length n has n factorial possible orderings. The comparison tree must have a vertex for each of those orderings, right? It must be able to determine that the array is in any one of those orderings. And so if we think about that then, so a tree, I guess it's a binary tree, I should say. Of depth k has in total 2 to the power of k plus 1 minus 1 vertices. And of those, right, half of them are actually in the bottom layer of this tree. And so I have to be able to fit all n factorial. I know that I need to fit all n factorial orderings in this number of vertices. So I need to make, right, the depth is the thing I'm trying to understand. It's like, how deep do I have to make this tree to make sure I have enough space to fit all the n factorial orderings in it? And so I'm going to need that 2 to the power of k plus 1 minus 1 has to be greater than or equal to n factorial to fit all the vertices on the tree. And so then I get that K, just taking the log of both sides, not worrying. Let's say the numbers are big, so we don't really have to worry about the 1. And in fact, we don't really even have to worry about the difference between 2 to the k plus 1 versus 2 to the k. But you can see that we basically get k plus 1 has to be greater than or equal to log base 2 of n factorial. And I argue that n factorial is greater than or equal to some constant times n log n. This step here because n factorial, which equals n times n minus 1 all the way down to n over 2, keeps going down to 1, is greater than or equal to n over 2 multiplied n over 2 times. Or maybe I should just write it n over 2 to the power of n over 2. And if I take the log, right, like if I just take the first half of this n factorial, each one of those elements is at least n over 2. And there's n over 2 of them. So definitely the n factorial is bigger than this thing. And if I take this, it's just going to be n over 2 log n over 2, which is just a constant times n log n. So therefore, we see that the depth has to be at least, so I want to write it as lower bounded, n log n, because k here is the depth. And so that means, right, the depth is in the worst case, how many comparisons do I have to do to get down to the answer? And so you can see that for any comparison-based sorting algorithm, there is an input array where the algorithm will make at least n log n comparisons. And that then tells us that any comparison-based sorting algorithm has a worst case runtime of n log n. Now, please don't, if that argument is a little bit confusing or a little bit vague, that's totally understandable. I'm trying to give a fairly complicated argument in a kind of intuitive way, but try and just not worry so much about the particulars of these calculations and just get the, hopefully extract the idea that we are kind of showing that no comparison-based sorting algorithm can do better than n log n comparisons in the worst case. Okay, so that's the end for this lecture. In the next one, we'll talk about medians. So thanks for tuning in. See you in the next one.